All right. So the topic for today's class is probability. Okay. Uh, in everyday life, like we frequently consider how likely something is to happen. You might ask questions such as, what is the chance of what is the chance of raining today? Or if you want to know whether, so that if you know the probability whether it's going to be raining today or not, so that you can carry an umbrella with you while you're driving. Or let's say, what is the chance of being struck by lightning? Or what is the chance of getting struck on a particular street in Karachi, for example, in the traffic? So that's the chance. The word chance means that there is a probability of something to happen. How likely or unlikely an event is to happen. Okay, so you can use numbers to give more accurate prediction. When you use the numbers, those are the probabilities. So in this topic, we are going to learn how to write the probabilities and of single event, more than one event, as fractions, decimals. Okay. So the first thing that we are going to discuss is the probability scale. So on a scale of 0 to 1, if something has a probability of 0, that means it's not going to happen. It's impossible. If something has a probability of 1, it is certain. There is no chance, like it is for sure that it's going to happen. So the probability of an event, if there is a chance present, has to have a probability between 0 and 1. If the probability is 0.5, that means it's 50%. Okay, 50%. So for example, if I toss a coin, and if it's a fair coin, the chances of getting a head or a tail is 50%. So there is an even chance. If the probability is less than 0.5, if the probability lies over here, you're going to say it's not that likely, it's unlikely that this event is going to happen. It has less chance. If the probability is between 0.5 and 1, you're going to say that it has more chance, it is likely to happen today. Okay, likely to happen. So probability is basically the study of chance or the likelihood of an event happening. A probability cannot be negative or greater than 1. It has to be between 0 and 1. Please remember this. Probabilities can be written as a fraction, can be written as a decimal, or they can be expressed as percentage as well, but not as ratios. Okay, so for example, the probability of getting a head is 1 upon 2, or you can write 0.5, or you can write 50%. Okay, this is how the probability is going to be expressed. Now, theoretical probability is equal to number of favorable outcome. Okay, so let's discuss these terms. Outcome means the result. Okay, so if I'm going to roll a dice, and it's a fair six-sided dice, the outcomes are going to be 1, 2, 3, 4, 5, and 6. These are the outcomes. Basically, these are the results when the dice is thrown. It can land on any of the 6 sides. The 6 sides have the 6 numbers. So these are the outcome. Okay. When you toss a coin, either you are going to get a head or a tail. That's an outcome. Getting a head is an outcome. Getting a tail is an outcome. And as and the all the possibilities or all the outcomes can be written as a sample space. Okay. Event means event over here. For example of an event is going to be that having a head. So having a head when a coin is tossed is an event. Okay. The probability that I will be late for my class, getting late for the class is an event. On the other hand, arriving early is an event. Okay. And the word random means that there is no biasness going to be associated with it. Okay. So fair means that the data is going to be collected randomly. It has to have random. It should not be biased. Like I can't influence. Random means that it can't be influenced by other factors. That is what random means. So a probability is calculated as number of favorable outcome divided by the total number of possible outcomes. Okay. For example, if I have a six-sided fair dice, the number of possible outcomes are 6. Okay. Either the dice can land on 1 or 2 or 3 or 4 or 5 or 6. So if I ask you, what is the probability of getting a score of 2 when a dice is thrown? So getting a 2 is one outcome. Getting a 2 is a favorable outcome. Okay. So probability of having a 2 is going to be 1 out of 6. 1 means that you can only have one face of the dice as 2. So that's the favorable outcome. Okay, divided by the total outcome, that's going to give you the probability. Okay, so the theoretical probability of an event is equal to the number of favorable outcome or successes, you can say, divided by the total number of possible outcome. Okay. Similarly, when the coin is flipped, you can have a head or you can have a tail. So if you write P of tail, that is simply the probability is simply abbreviated as P of tail. That means probability of getting a tail when a coin is flipped once. That is going to be equal to so when I flip a coin, how many outcomes are there? There are 2 outcomes. Either I can get a head or a tail. If I want a head, if I want a tail, there is only one tail. Okay, so that's 1 out of 2. So the probability comes out to be 1/2 or 0.5. Okay. Okay. Now, if the probability of a tail is 0.5, can you guys tell me what is the probability of a head is going to be? What is the probability of getting a head?
0.5.
That's also 0.5. So 1, remember that the total probability is 1. Okay. If you minus the probability of tail, you can get the probability of head. That is 1/2. Or we could have done it directly as well. Okay, if the probability of getting a 2 is 1/6, then what is the probability of not getting a 2?
5.
So if I'm not getting a 2, then what am I getting? I'm getting 1. I can get 3. I can get 4. I can get 5. I can get 6. So that are 5 options out of 6. So the probability of not having a 2 prime, is going to be 5/6. So remember this, that the probability of an event not happening is 1 minus the probability of that event happening. So if there is I can tell you another example. If there is a 20% chance that I'm late for the class, so what is the probability that I'm not going to be late for the class? If there's a 20%, if there's a 20%, yeah, if there's a 20% chance that I'm getting late for the class, then there's a 80% chance that I'm not going to be late for the class. So if the probability of me getting late is 0.2, then the probability that I won't be late is going to be 1 minus 0.2, that is 0.8. Okay, now let's look at probabilities of single event first. A fair 10-sided dice containing the numbers 1 to 10 is rolled. So it's a special dice that has 10 faces. Okay. And it's a fair dice, meaning no biasness. A fair dice is a dice that in which all the options, all the outcomes will have the same probability. That's why it is fair. So fair also means unbiased. So if it's a fair 10-sided dice, there are 10 outcomes from 1 to 10. You need to find the probability that it land on an even number. So from 1 to 10, how many even numbers are there?
5.
5. So probability that it is going to land on an even number is going to be
5 over 10.
5 over 10. That is 0.5. What is the probability of it landing on a prime number? So you're going to consider how many prime numbers are there.
3 over 10.
Prime numbers, how many prime numbers are going to be there?
3.
The first prime number is 2, then 3, then 5, and then 7. So that's going to be 4 out of 10. So 4 out of 10 means 2 upon 5. Okay, what is the probability that a number that it lands on a number that is a factor of 20? So from 1 to 10, how many numbers are factors of 20? First think of the sample space. From 1 to 10, 1 is the factor of 20, 2 is a factor of 20, 4 is a factor of 20, 5 is a factor of 20, and 10 is a factor of 20. 5 times 4, 10 times 2, and 1 times 20. So there are 5 outcomes out of 10. Okay, so that's going to be 0.5. All right. Let's look at this example. Have you played cards ever? Have you guys played cards?
No.
No?
Yes.
Okay. Those who have played cards would know that a standard pack has 52 playing cards and there are 4 suits. So there are 4 types of cards, or you can say there are 4 categories. One is the hearts, one is the diamond, one is the clubs, and one is the spades. The hearts and the diamonds are red in color, and the clubs and the spades are black in color. In every category, in every suit, there are 13 cards. 13 cards. Okay. So in each category of the card, for example, heart, there is going to be one ace. There is going to be ace of hearts, ace of diamonds, ace of clubs, ace of spades. There is going to be a king. There is going to be a queen. There's going to be a jack. And then there are going to be numbers 10, 9, 8, 7, 6, 5, 4, 3, and 2. These are your 13 cards. There is no card having a number of 1. This is the order in which the highest card is the ace, the second highest is the king, and so on. 2 is the smallest card, and these are the 13 cards present in every suit. So there is going to be a ace of diamond, king of diamond, queen of diamond, jack of diamond. Similarly, there is going to be a ace of clubs, king of clubs, jack of clubs, and so on. Similarly for the spades. Is this thing clear? So what is the probability of getting a black card?
26 over 52.
Yeah, so there are 26 black cards. So the probability of getting a black card is 26 over 52. That is 0.5. What is the probability of getting a red ace? How many red ace cards are going to be there? Red ace. So
2 over
it
52.
can be an ace of hearts or an ace of diamond. So 2 out of 52. What is the probability of getting a diamond card? So you have a standard pack of card, okay, and you are randomly drawing one card. Now I'm asking you, what is the probability that the card that you are going to pick is going to be a diamond card?
13 over 52.
13 over 52. That's correct. You can always simplify down the probabilities. 13 over 52 is 1 upon 4. Okay, try the next one. So what is the probability of a card that is not a diamond?
3 over
Sorry?
3 over 4.
Yeah, probability that it's not a diamond. So in a standard pack of 52 cards, if 13 cards are for diamond, so the remaining, say 39 cards are not the diamond cards. So 39 divided by 52, that's going to be 3 upon 4. Okay, that's one way to go about it. Second math, or you could have done this. Probability of not a diamond is 1 minus the probability of having a diamond. The probability of having a diamond was 1 upon 4. So 1 minus 1 upon 4 is also 3 upon 4. Make sense? Are you guys clear with this?
Yes.
Yes.
Okay. Okay. Now in the probability chapter, we are also going to be looking at mutually exclusive events. Mutually exclusive events are those two events that are mutually exclusive. That means that they cannot occur at the same time. So if I toss a coin, either I will get a head or a tail. They can't occur at, they both can't occur at the same time. Okay. Similarly, if I have a bag of few color balls, let's say I have a bag of uh, red balls, 5 red balls, 3 blue balls, and 6 green balls. Okay. So if I close my eyes and I try to pick up the balls randomly, if I pick up one ball randomly, okay. So if that particular ball is a blue ball, it can't be a red ball. Either it is going to be a blue ball or a red ball or a green ball. It can't have two colors together, right? So these are mutually exclusive events. Okay, mutually exclusive event. So mutually exclusive events means that if you want, okay, two events are mutually exclusive if they cannot happen together. So for example, a bag contains 5 red, 6 blue and 9 green marbles. A counter is selected from the bag at random. A counter means a single counter. What is the probability that the counter selected is a blue or a green? So you want to find the probability that it's a blue or a green. Okay, the probability that it's a blue or a green. Probability that it's a blue or green. So either the counter can be blue or the counter can be green. It can't be both at the same time. So you are going to calculate the probability of getting a blue counter or the green counter, and you're going to add them, because if you add them, then the chances are going to be increased. For example, if your task is not to find the probability of blue counter only, because if you want to find a blue counter, your chances are going to be less. If you want to find the only green counter, your chances are going to be less, because that is a single event. Okay, but if you increase the possibility, if you say that okay, I am fine with having either a blue counter or a green counter, so that means that when you pick up one counter randomly, you will have this satisfaction that okay, if not blue, then it is going to be green, or if it is not green, then it can be blue. So your chances are increased. So basically your probability is going to increase. So having a blue counter over here has a probability. What's the probability of getting a blue counter? There are 6 blue counters. How many total counters are going to be there?
20.
20. So if you add these values, there are 20 counters. So if you pick up a counter at random and it turns out to be a blue counter. Okay, so the probability is 6 out of 20, and the probability of getting a green counter is 9 out of 20. This is one way to go about this. It's going to be 15 out of 20. Okay, that's 3 upon 4. Or you could have done this. Instead of writing this equation like this, you could have just simply added, because you know that the two counters are mutually exclusive. The two counters colors are mutually exclusive. They can't happen at the same time. So if you want a blue or a green counter, the simple working could have been that you count the total numbers of blue and the green counter. So that adds up to 15 and out of 20. So simply you can do it in one step as well. Okay, guys, just make a correction over here. This is going to be or. Probability of A or B. Okay, A or B. Is this example clear to everyone?
Yes.
Okay. Okay. Adam picks a number at random between 1 and 50 inclusive. What is the probability that he picks a prime number? What is the probability that I pick up a prime number? How many prime numbers are between 1 and 50? I have been given a chance to pick up a random number between 1 and 50, but that has to be a prime number. So simply the question is asking the probability of getting a prime number. What is the probability of getting a prime number? So for that, you need to find out how many prime numbers are there going to be between 1 and 50. So how many prime numbers do we have between 1 and 50? Starting with 2, then the next is 3, then the next is
5.
5, 7, 11, 13, 17, 19, 23, 29, then 31, 37. Is 39 a prime number?
No.
No. 41 is a prime number.
Yes.
Then 42 is not. 43 is a prime number. 44, 45, 46 are not the prime number. 47 is a prime number. 48 is not. 49 is not. 50 is not a prime number. So these are the prime numbers. So you can just count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There are 15 numbers out of how many numbers? Out of how many numbers?
50.
50. So the probability turns out to be, you simplify this probability, you get 3/10 or 0.3. Okay, does this make sense to you? Okay, now the next person, Orahan, picks a number at random between 1 and 100 inclusive. He says that the probability of picking a prime number from 1 to 100 will be twice of probability of picking a prime number from 1 to 50 inclusive. You need to show that Orhan is wrong. How can I show that he is actually wrong when he says that the probability of getting a prime number from 1 to 100 is going to be double?
We can just simply count.
You can simply count. So how many prime numbers are there between 1 and 100? So from between 1 and 50, we know that, right? We know these are the prime numbers. So just count the prime numbers after 47. After 47, the next prime number is going to be 53, right? After 53, 59 is a prime number. Then,
So is it 51 a prime number?
sorry?
51.
51.
51 is divisible by 3.
51 is divisible by 3. So it's
Oh,
not
okay.
a prime number. So 61 is a prime number. Then 67. Then 71. 73. Then I believe 79. After 79, 80, 81, and 82 are divisible. So 83. 84, 85, 86, 87. What about 87? 87 is also divisible, I believe. 87 is
Yes.
divisible by 3. 3 times 29. So 80, after 83, 89, 90, 91, 90. What about 91? Is 91 a prime number?
Yes.
Yeah. What about 93?
No.
No.
93 is not a prime number. Okay. Then I think 91 is also not a prime number. 91 is not a prime number because it's divisible by 7. You can check. So 90 after
Oh, yeah.
after 89,
97.
97 is going to be the prime number. So now you may count the outcomes. We know these were 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So the probability of having a prime number between 1 and 100 inclusive is 25 out of 100, that is 0.25. Okay, so 0.25 is not twice the 0.3. You can write this down in the statement. I don't have space, so I'm not writing it. So 0.25 probably is not twice of 0.3. Okay, so you can conclude that yes, Orhan is wrong. Okay, is the example clear?
Yes.
Okay, then we have the probability of an event not happening. As I mentioned, if you know the probability of an event happening, you can just subtract that probability from 1 so that you get the probability of an event not happening. So the probability that Naeem's bus is late is 1 upon 8. What is the probability that Naeem's bus is not late? If I want to find what is the probability that his bus is not late, bus is not late, then I'll have to calculate it like this: 1 minus probability that the bus is late. So 1 minus 1 upon 8 is going to be
7 over.
7 over 8. 1 minus 1 upon 8 is going to be 7 upon 8. Okay, I want you guys to try the next one. So if I want to if there are 3 options over here that Salma has, she can either travel by bus, car, or bike. So if you want to find the probability that she travels by bike, that is going to be 1 minus the probability that she is not traveling by bike. So when she is not traveling by bike, then she is traveling with either the car or the bus. So you're simply going to add the probabilities. So that's 0.5 plus 0.2. Okay, so 1 minus 0.7, that's going to be 0.3. Everyone is getting the same answer? Abdul Rahman, Zona, are you also getting the same answer?
So can we simply plus the probability of 0.5 and 0.2 and the remaining is the answer?
Yeah, that is what I have done. That I have simply added these two and subtracted it from 1. I've just I've just shown my answer in a proper way by writing all of this. Otherwise, the logic is the same. Okay.
Yes.
Okay. Now try this one. All right. So the table shows the probability of getting sum of the scores when a biased six-sided dice is rolled. So the dice is biased. That's why you can see that the probabilities of each outcomes are not the same. Okay, because it's a biased six-sided dice. Now, what is the probability of getting a 4? So if this is the only outcome left, you can just add up all the probabilities and subtract from 1 to get this probability. So probability of getting a 4 is going to be same as 1 minus probability of not getting a 4. So when you're not getting a 4, you can either get 1 or 2 or 3 or 5 or 6. So you just add all these probabilities. So what's the answer?
0.11.
0.11. Is everyone getting the same answer?
Yes.
Okay. Abdul Rahman, do you have any questions till here? Abdul Rahim?
No.
Zona? All clear? All right. The next thing that we are going to discuss is the concept of experimental probability. Now, for example, like we did theoretical probability because when we are tossing a coin, okay, we know that there are two options only. And if it's a fair coin, the probability that it's going to land on a tail, I'm going to get a tail is 1/2, and the probability that it's going to land on a head is 1/2 as well. Okay, but let's say I tossed the coin once and it landed on a head, and then I tossed the coin again, and you know what? It landed on a head again, and then I tossed the coin thrice. It landed on a head, and then I tossed the coin again the fourth time. Then it landed on a tail. Now, if I just did it 4 times, I'm doing an experiment. I'm performing an experiment over here. And what I observed was that it landed 3 times on head and 1 times on tail. Will I say that the probability of getting a head is 3/4 then? And the probability of getting a tail is 1/4. Okay, now these probabilities are different because it's the experimental probability. It's the experimental probability. Are you getting my point? There was a theoretical probability of getting a tail when you flip a fair coin, that is 1/2. Now, does that mean that if you flip a fair coin twice, you will get one head and a tail? That's not true, because you can get a tail again, or you can get a head twice. So it's not true. Theoretical probability only gives you an estimate of how likely an event is to occur. Okay, it just tells you, it's just help you predict. In reality, the outcome of a trial may not be exactly as predicted. If I'm predicting that it's going to rain tomorrow, does it necessarily have to rain tomorrow? No, it may not rain tomorrow. So the outcome of a trial may not exactly be exactly as predicted. Now, for example, we got a data of rain for a month, and in Karachi, let's say there were 4 days out of the entire 30 days that it has rained, and my weather forecast was showing that it's going to rain for 15 days, but in actually it rained 4 days. Then that's your experimental probability. Okay, so that's the idea behind it. So experimental probabilities are calculated using relative frequency. I'll tell you what this means. Just a second. So relative frequency is basically the number of favorable outcome divided by the total number of trials. Now the word trial is over here. Okay. The outcome of a trial may not be exactly as predicted. Remember, in the experimental, uh, in reality, the outcome of the trial may not be exactly the same. So relative frequency means number of favorable outcome divided by total number of trials. What happens is that your experimental probability gets closer and closer to theoretical probability for larger number of trials. The more times you repeat the trials, the closer the to theoretical probability this becomes. So let's say if I were to if I were to flip the coin 200 times, then I would be getting close enough to getting equal number of heads and equal number of tails. Okay. If I am going to roll the dice 700 or 800 times, then I may be getting the outcome 1, 2, 3, 4, 5, and 6 equally likely. And then if you calculate the probability, so it's going to be closer to 1 upon 6. So the higher the times you do the trials or the experiments, the closer you get to the theoretical probability. So let's consider this example. Person A, B, and C are testing a coin that they think may be biased. Okay. So person A, what he did was he flipped the coin 10 times. And out of the 10 times, he got 3 times head and 7 times tails. Person B did it 50 times. He got 26 times head and 24 times tails. Person C flipped 100 times. He got 46 times head and 54 times tails. So whose results are more reliable? Give a reason for your answer. What do you think? Whose results are more reliable and why?
C,
Why
because
C?
did it most times.
Yes, she repeated the experiment the most times. So the person, I don't know whether it's he or she, but this person's data is more reliable because he did the he did the experiment or the trials most times. So you are going to say person C, and because he or she repeated the experiment the most times. She repeated the experiment for most time. Okay. Now part B, using all the data in the table for all the 3 people, calculate the relative frequency for flipping a head. Now what is the relative frequency? Relative frequency is number of favorable outcome divided by the total number of trials. So we are going to be calculating the relative frequency for flipping a head. So, and we are going to do this for each person. Oh, we have to do it for all 3 people. Sorry, my bad. We have to do it for all 3 people. So all 3 people, how many times did all 3 people got the head?
75.
So number of heads by all 3 people is going to be 3 plus 26 plus 46, that is 75, divided by the total number of trials. What are the total number of trials? Sorry, total number of trials. 10 plus 50 plus 100, that is 160. So the relative frequency for the number of heads is going to be 75 upon 160. I'm getting 0.47. Is that correct?
Yes.
Okay, now part C says, is the coin likely to be biased? Explain your answer. How would you decide on the basis of probability whether the coin that they were using is a fair coin or a biased coin? Initially, they thought it is a bias coin. So person A did the experiment with the same coin, person B did the experiment, person C did the experiment. And as they are doing larger number of trials, you can see that the outcomes are getting closer and closer. So the probability of getting a head and probability of getting a tail is roughly
Uncertain.
0.5. Okay, and the theoretical probability of getting a head and a tail is 0.5. So if the relative frequency is close to the theoretical probability, then you're going to say that the coin is not likely to be biased. Okay, it is not likely to be biased. So the question was, is the coin likely to be biased? You're going to say no, no, and then you're going to give the reason. The relative frequency is close to the theoretical probability was 0.5. Okay, so the coin is not likely to be biased. Okay, has everyone understood this question? Do you guys have any questions till here?
So what if in all three trials the heads were the most? So we would have written that आपका is the coin is likely to be biased
So what's the condition when the number of heads are
the most in all three.
even no, that's not the right way to predict whether the coin is biased or not. So if person A was getting more heads, person B was also getting more heads, and person C was getting more heads, more head doesn't mean that the coin is biased or unbiased. The For lesser number of trials, you may get the probability not close enough to theoretical probability. We know that the theoretical probability of getting a head is 0.5. But over here, if you see the probability of getting a head for person, the relative frequency for getting a head is 0.3 for person A and 0.7 for person B. Is he close enough to the theoretical probability? No, because he has gone for less number of trials. This person increases this person increases his number of trials, and he found out that 20 there are 26 heads and 24 tails. Person C did it 100 times and he got this result. Okay, now when the results when the results of the relative frequencies are getting closer to closer to the theoretical probability was 0.5. Okay, so this probability is 0.46 and this probability is 0.54. They are much closer. So if the experiment would have been done more number of times, they might get to a probability relative frequency closer to theoretical probability. So if the relative frequency gets close enough to theoretical probability, we are going to say that the coin is not biased. It's fair. Okay.
Yes.
Okay. All right. So I'll continue from here in the next class. Okay.
Yes.
Take care. Allah Hafiz.
Love is.